stuff, I suppose. So we're going to start off with, I think, chapter 12, I believe, and maybe it's 13, one of those. We're going to talk about chemical kinetics. So in this chapter, we're going to talk about kinetics, which will have several formulas and stuff before we get into a lot more of the conceptual stuff, which starts with really kind of the next chapter. So kinetics is really about how fast or slow a reaction takes place. We're going to do some calculations in this chapter to determine, what affects a reaction's rate, or we'll see things that affect a reaction's rate. So there's really sort of two areas of chemistry that we oftentimes will talk about. One is thermodynamics. And thermodynamics, you talked a little bit about at Chem 50. It was all that delta H stuff, that enthalpy. That's one part of thermodynamics, which is like the heat and energy associated with a reaction. In this class, we will talk about some of the rest of the thermodynamic sort of properties like entropy, Gibbs free energy and stuff like that. So after we get through all the titrations, buffers, and all that, we will roll into some more thermodynamic type of stuff. The ultimate goal a lot of times of thermodynamics is to basically answer a fairly simple question, which is whether or not this reaction will occur spontaneously. And when we talk about spontaneously, and we'll talk about when we do get to that sort of chapter as well, sometimes people have a misconception about what spontaneity means. So sometimes people think if we say a reaction is spontaneous, it's like going to happen like super fast. And really, that is not really what we were talking about when we say like a reaction is spontaneous or not. What we're saying is if it's spontaneous under those particular conditions, that reaction will simply take place. It could take place really fast. It could take place super slow. There's lots of reactions that actually are spontaneous that take place very, very slowly. So thermodynamics sort of answers that question. And again, we'll talk more about that in a later chapter about, does a reaction take place really is what you're looking at. To sort of answer the question of how fast or how slow a reaction takes place, that's really what kinetics is all about. So kinetics is really the understanding about how fast or slow a reaction will take place. And as I said, we'll talk about some factors can affect that along the way. Now, in normal cases, when we talk about a rate, that's really, something over a unit of time, right? So like when you're driving, that's how many miles per hour you are traveling. What that basically means when you're doing 60 miles per hour is if you put it on cruise control in 1 hour, you could go 60 miles is basically what that means, right? So when we talk about rates with reactions, what we oftentimes look at is the change in the concentration over a period of time. And most of the time, the concentration unit that we're dealing with is what we've been talking about a little bit here, which is molarity, which is our moles per liter. So we oftentimes will look at the change in the molarity over really the change in time. And that's why typically reaction rates have units of something that looks like this, which is molarity per second. So basically how the concentration is changing over a period of time. When we look at a reaction such as this, as A goes to B, and A are our reactants, yes, and these guys are our products on this side. And obviously the reactants are our starting materials in a chemical reaction. The products are obviously what is formed as a result of the chemical reaction. When this reaction takes place, we would expect this reaction to go from A to B, which means over a period of time, would we expect the amount of A to increase or decrease? It should decrease, right? In order to make products, you need the reactants basically to come together to make those products. Thank you. And by the same token, because this reaction is really heading to the product side, it's basically a one-way street here. It's all heading towards the product side. We would expect the amount of products to start to increase over a period of time. So what we should expect to see is sort of that decrease in the reactants. At the same time, we should start seeing an increase in the products that are being formed. And we could write what is sometimes referred to as a rate expression to help us sort of explain what's going on. So for this particular reaction, we could write the rate is equal to minus the change in concentration of A over the change in time. So typically, if you see the delta symbol, that means change. And if you see the brackets, that means concentration. And that usually is, again, molarity is usually what we're talking about. Doesn't always have to be molarity, but obviously that is probably the most common unit of concentration that we deal with. We do see the negative here, and the negative is put in there because the amount of reactants are decreasing with time. So in kinetics here, and when you typically calculate the rate of a reaction or the average rate of a reaction, that is typically a positive value. So when you calculate kind of the rate of the reaction, it's typically a positive value. So when we do the change in A in this particular case, that really is the concentration of A kind of at the end minus the concentration of A at the beginning. In this particular case, our initial concentration actually will be larger than our final because it's decreasing. That's going to give us a negative value, right? When we do that calculation, that negative and that negative right there will then turn our rate into a positive number. So we do want to make sure you do sort of final minus initial when you're calculating something like that. We could also write a rate expression here for B, which looks something like this. The rate is equal to the change in concentration of B over the change in time. In this case, because it is the products and we're expecting them to increase with time, we do not have the negative, so it is a positive that's there. And in that case, when we think about the change in the concentration of B, which is our products in this example, that would be the concentration of B at the end minus the concentration of B initially. In this particular case, the concentration at the end is actually larger than your initial because you're making products. So you will get a positive number when you kind of calculate that part of it. Obviously, the change in time is basically beginning time, ending time, the difference between the two. Typically speaking, most of the time, a lot of times it is seconds. And that's because we just think logically, if you're in the lab, a lot of experiments happen relatively quickly and we measure them in seconds, maybe minutes and stuff like that. But it really can be any unit of time. It could be minutes, hours, days, whatever it may be. But most commonly it will be seconds in terms of that unit because that's most commonly sort of what we deal with. Any questions on that there? All right. So how can we measure some of these things? We can visually see what's happening as well. Here's just a visual representation of that at the very start of the reaction, which is here. It's pretty much all black circles, which represent A. There's really no red circles in there, so we have really no products. And as you can see, as time sort of progresses here, we start to see the disappearance of our reactants, kind of the black circles. We start to see the appearance of our red circles, which represents our product. And at the end, obviously, we have a lot more products than we started with. Graphically speaking, if you learn nothing in kinetics, they love graphs. Yes, there's lots of graphs in kinetics. You'll make a lot of graphs. You'll see a lot of graphs. Sometimes as you go through some of the homework problems, the only way to solve it is to make a graph. So just keep that in mind as you kind of go through some of that stuff. But graph-wise here, this is basically our time. And we can see at time 0, we pretty much have no products, all reactants. And then obviously, as we start making some products, we will lose some of those reactants until sort of the reaction is complete. Now, how can we measure sort of the change in the concentration versus time? Well, if we have something that is a color type of reaction, in this particular case, the Br2 is that pretty color. Everything on this side is basically colorless on that side. So at the beginning of this reaction, when we add the Br2 and a little formic acid, which is the second thing that's there, we get this nice kind of reddish color. And as time goes on and more products are being made, obviously our color gets lighter and lighter until it kind of gets colorless and when the reaction is basically complete. We could use something like spectrophotometry, like you'll be doing there in part 2 of the experiment, and we'll do several times as well. And use something like Beer's law, which is A is equal to BC. A is the absorbance. B is Beer's constant. C is the concentration. Sometimes people will use A is equal to EBC, and basically this is the molar absorptivity coefficient, and B is the path length. Most of the time, the path length is really the size of the cuvette you use, which is like 1 inch, or in most cases, or 1 centimeter. And so a lot of times in here at this school, we kind of use this version most of the time, Beer's constant and our concentration. So there is a relationship between the color of the solution and the absorbance value. How does all those spectrophotometry work? You have a light source, which you shoot light at a specific wavelength. And basically it goes through your sample, and you measure one of two things. You either measure absorbance values, which is how much light is being absorbed by the sample, or you measure percent transmittance, which is the ratio of how much light you shot into how much light reached the detector, basically. Absorbance is equal to minus the log of the transmittance, although we don't use it too much. But most of the time we do measure absorbance values here. Now, if the solution is a dark color, will it absorb more light or less light? It will actually absorb more light. So the darker the solution, the higher absorbance values you will get, because the light will be able to pass through really to hit the detector. So a lot more will be absorbed. The kind of colorless or lighter the solution, the lower the absorbance values here. So if we were following absorbance here, we would actually see it start to decrease as we head in this direction if we were taking measurements all the way through the experiment. When we do anything that involves sort of this sort of process here, we always want to find the maximum absorbance. And usually in the old days, you would manually put your solution in and measure it at many different wavelengths. They have nice technology now that you press a button and it does all the wavelengths at once. And it spits you out a graph that looks something like this. And what you have here is absorbance on the left here and on the Y, and then wavelength on the X. And you really do want to kind of pick the maximum wavelength to set your machine to. Why would I perhaps not want to pick a wavelength down here? What's going to happen when I run my samples? You're going to get errors, because basically you only have about that much absorbance, right? So you put some samples, it's going to absorb over here. You're going to get like an error on the machine. Over here, I can measure values that range all the way through all those absorbance values, which means you're probably going to be able to run all your samples with no problem. Yeah. So we'll do this, I think maybe part 2 if we do it, or definitely in the first experiment. But one of the things that you commonly do when you do these procedures, like I said, is usually you'll maybe take your darkest colored one and use that and put it in, and then it does all the different wavelengths and you pick the maximum wavelength. So all your other samples should run there. Or perhaps if you're diluting a stock solution, you just take some of the stock solution, which should be the darkest color that you have to do that. By the way, if the solution is red in color that we see, would I set the wavelength of the machine to red? You would not. Actually, the color that we see in the solution is actually the complementary color to the one that's being absorbed, the wavelength of light that's being absorbed. So sometimes people are like, wait, it's red, but I'm setting it like maybe in the greenish or bluish area, you know, in terms of a wavelength. So the color that we see in a solution, we would actually set the machine to the complementary colors wavelength, because that's the amount of light that's being absorbed. Any questions on any of that there? So how does this really help us? We can, over a period of time, measure absorbance values and then use something like Beer's law to convert those absorbance values into concentration values. So by doing that, what we're able to do basically is figure out the change in the concentration over the change in time by just using the absorbance values and the Beer's constant sort of relationship there to allow us to do that. Any questions on that there? All right, so as I mentioned in this particular example, the change in the concentration of the BR2 would obviously be proportional to the absorbance value So higher absorbance, higher concentration of Br2. As the absorbance drops in this example, we would see a lower concentration. So if we ran an experiment like this, there's a couple of different types of rates that we sometimes come across. And one is the average rate, which is basically the change in the concentration, in this case of the Br2 over time. Once again, Br2 being a reactant. So we do have that negative there. And we would expect this concentration to be decreasing with time. And again, that will turn our average rate into a positive number. So again, this number here should be smaller than this number, which will be larger. So that will give us, again, a negative, with that negative turning this guy into a positive number. There's also instantaneous rates, which is a rate for a specific period of time. You could find that, for example, like here on the graph, by taking the slope of the tangent of that line, if you were to graph it. So I sort of explain this like when we are driving. So for example, say you're driving to Arizona to go catch spring training this weekend, and you drive maybe like, you know, at some point 65, some point 70, 75, 90-ish as very low periods of time. Maybe you drive that, right? So there's a certain period of time, if you were just to sample it, right? You may be going for that instantaneous part of time. Maybe you're doing 85, and hopefully there's no cop behind you, but you're doing 85 at that little period of time. But if you average out your entire trip, maybe on average, you drove an average of 70 miles per hour or 65 miles per hour or something like that. So average rate is oftentimes what we kind of look at as kind of what's happening over the whole period of the reaction. But if you did want to sort of just take a window peek of it, you would see that the instantaneous rate for that time may be different. It may be higher at some points during the reaction, it may be lower at some points during the reaction. And that's why we kind of look at the average rate over the whole period of time. And that's kind of what we see here if we look at the data for this particular experiment. If we look at sort of like the instantaneous rates, you can see it really does sort of vary depending on that period of time. Again, the reaction may start off really fast because there's a lot of reactants there to start reacting. But as the reactants get used up and you start making some products, it takes a little longer for more reactants to find each other. So maybe the reaction will slow down. Maybe even towards the end of the reaction, it will slow down even more along the way. But there is a relationship that we can write that is a constant for the entire reaction, and that is the rate constant, which is this column here. And you can see that for the most part, those numbers are relatively constant. So lowercase k is the rate constant. And I say lowercase k because, as we'll talk about for pretty much most of this semester, capital K is the equilibrium constant. So there is a difference between capital K and lowercase k. In this chapter, we're dealing with lowercase k, which is the rate constant. You could write something like this, which is sometimes referred to as the rate law. And if you solve for the rate constant by dividing the Br2 to the other side, that will give you your value of 3.5 times 10 to the minus 3 in this particular case. So a lot of times what we will look at as well for a reaction is what the rate constant is. You could kind of look at the rate constant as kind of how fast or slow the reaction will take place. So sort of a larger value for the rate constant means it will actually occur a little bit faster, that reaction. A smaller value for the rate constant means that we will have the reaction occurring a little bit slower along the way. And we're going to talk about how you calculate that, obviously, here in a bit. Now, what happens if we do have a reaction where perhaps it has no color? So if we did a reaction where there really is no color, either no products make color, no reactants make color, could we use spectrophotometry like we were just talking about to help us with that? So let's say we did a reaction and everything's colorless. Would that work, that process? It would not work because all your absorbance values would be 0, right? Because there's no color, there would be no light being absorbed. So that process works really well. That what we were just talking about for obviously anything that has any type of color associated with it. But perhaps something like this where you have no color and you are making a gas, We can use our good friend. Is that rain? That is rain. I was thinking like somebody was flying over. Oh, terrific. I know. I think we should take a field trip outside. I don't know. All right. They say it's snowing. We'll go make some snowman out there. I don't know. It'll be okay. Hopefully you brought a shovel to dig your car out later. I don't know. It'll be okay. All right. I'm just like, I'm hearing something louder and louder, Gavin, at it. All right. All right. It's only weather. Blizzard warning. We'll be okay. It is California, I think. All right. So PV equals nRT is our ideal gas law. We remember that one. When we do use the ideal gas law, it does need to be in certain units, right? So pressure needs to be in atmospheres. That sounds like a good one. Volume is liters, yes. N is moles. R is the gas constant, which is 0.08206 liters atmosphere, Kelvin mole, and temperature needs to be in Kelvin, right? Added to 73 to your Celsius. So remember that you do need to do all these units when you use the ideal gas law, and obviously common other units of pressure, millimeters of mercury and torr. That's a 760 is the conversion there, right? So 1 atmosphere is 760 millimeters of mercury or a torr. Now, if we take the ideal gas law and we do a little rearranging and we solve for N over V. So N over V would equal P over RT. The units of N is moles. The units of V is liters, and moles per liter is the molarity. So when you do solve the ideal gas law for mole N over V, you're actually solving for the molarity of a gas, which seems kind of weird, but that's actually what you're doing. And what that means is if we look at sort of what's left of the ideal gas law, that R is a constant. And if you ran this experiment, you most likely are going to run it in the room that has the same temperature. So the temperature is not going to change, which means ultimately what we would need to do if we're doing something with gas is simply follow the change in pressure over time. And by following the change in pressure over time, we can use something like the ideal gas law to relate it back to how the molarity of the gas is changing over time. And that's what we see here, basically. That's the change in the concentration of O2 over the change in time, which means a very simple experiment would be just to watch the change in the constant, the pressure over time. Yeah. And where? Right here? Is that what we're talking about? Yeah, it's P over RT. It's basically this right here, P over RT. Yeah. Other questions? So in this particular, yeah. Yeah, so this is one alternative. This would work obviously really well for something that produces a gas, right? Or even if you had a gas to start with, right? You would need some type of gas for this to be working. Because if you didn't have a gas, you would have no pressure, right? So again, much like the spectrophotometry, which would not work well if you had no color in your solution, using the ideal gas law obviously wouldn't work very well if you didn't produce any type of gas. We're able to do this in this experiment because we did produce a gas. And really, that is the only gas that's in this reaction, right? So any pressure that happens in this reaction is a result of the O2. And the only way that the O2 could cause pressure would be if it was made, right? So that's how come this would actually work. Yeah. It is, yes. Yeah. 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 Yeah, so in both of these experiments, what you typically would do is you would take measurements like if you were doing it manually, you would do maybe measurements every 5 seconds, 10 seconds, 20 seconds, something like that. Something that you would be able to, write it down and do it. Nowadays with technology, they could take pretty much the reading every second, basically. So what you would do is you would take a bunch of readings using technology to help you out there. It would be able to take readings basically every second. So it would take a pressure reading every second. And you can make a graph like we saw on the previous page where you would see, in this case, you would actually see the pressure start to go up, right, over time as it's making the O2. But you would definitely take readings of either pressure in this case or absorbance in the other case at certain periods of time, kind of consistently throughout the experiment. Other questions? I know, I'll get the boat. We'll be all right. All right. All right, so let's talk a little bit more about the rate expression here. If we do have a reaction such as 2A goes to B, we do have to take into account our favorite thing, which is stoichiometry, and that is the mole-to-mole relationship here. And if we do not do that, our calculations will be wrong, right? Because the stoichiometry also affects, obviously, how much products produce and those type of situation. So when we write the rate expression for a reaction like this, what we could do is actually take 1 over the coefficient, and that will give us the correct sort of stoichiometry involved there. So that's what we see here. The rate is equal to negative because A is a reactant, so it's again decreasing with time. 1 over 2 is basically 1 over the coefficient, which is 2. And again, our change in the concentration of A over the change in time. When we go to our product side here, once again, the product's going to be positive because it's increasing with time. The coefficient here is 1. So basically that's 1 over 1, which is 1. And usually we don't put 1 in chemistry. And that's why that's just a change in concentration of B over the change in time. So in general, you could write a rate expression and you could actually set all those things equal to each other. And the nice thing about the rate expression is this: if you essentially know basically just one piece of information about the reaction, maybe you know the average rate, or maybe you know for A, how much the concentration is changing versus time, or even maybe you know something about a product, how C is being produced versus time. You basically could figure out using the rate expression how everybody is changing that reaction over a period of time. Now, once again, when you do this, this number here should end up being a positive number. And again, you want to make sure you do, like we talked about, kind of our final minus initial, because that will give you that negative value. You can use it like this if you're just looking at, for example, D and A. You could just pull out those things and write individual ones for A and D. And why this is helpful is this rate right here and this rate right here. Is that a different number or the same number? Are they in the same reaction? Yes, they're in the same reaction. And that's the average rate for the reaction, which means those numbers are the same. So as long as you know basically one piece of information like this, you can figure out the average rate for the reaction. You then can use the average rate for the reaction to figure out how maybe D is changing with time. So if you incorporate the 1 over the coefficient, it will kind of take care of the stoichiometry for you. And hopefully it will prevent you from either multiplying or dividing incorrectly. You can also just do the stoichiometry part of the calculation like normal, like a mole-to-mole relationship, like a normal stoichiometry problem. And then at the end, incorporate basically the kinetics part of it, the time and all that. So you can break it up that way. But sometimes it's a little easier just to kind of, in this case, to do it all together. Again, so you don't miss multiplying or dividing incorrectly. All right, so why don't you write the rate expression for this one and see what you come up with. So we could write here the rate is equal to, we'll start here on the reactant side, coefficient is 1. We are going to put a negative because it's a reactant. The change in the concentration of CH4 over the change in time. That would then equal our coefficient here for our other reactant is a 2. So that would be minus 1 over 2 change in concentration of O2 over the change in time. Now moving to our product side, we should be increasing with time. So these are going to be positives. So that would be the change in the concentration of CO2 over the change in time. And once again, here we do have a coefficient of 2. So that's going to be 1 over 2 change in the concentration of H2O over the change in time. Any questions on that one there? All right, so let's take a look at one maybe where there's some numbers and see if we can do some calculations here. So why don't you give it a go? For this reaction, the change in the concentration of I minus changes from 1 molar to 0.868 molar in the first 10 seconds. Calculate the average rate for the first 10 seconds and how the concentration of H plus over the change in time is changing. I don't know if your delta T is on your handout or not, but we're looking for the change in concentration of H plus over the change in time, what that equals. Just over the change in time, yeah. So I don't know if that's still on your handout or not, but add that to it. That's what we're looking for, yeah. All right, let's take a look and see here. So in this particular case, we are given information about I minus. So we can write the rate expression for that guy, which is the rate is equal to -1/3 because of the coefficient. And again, it's a reactant. The change in the concentration of I minus divided by change in time. We're ultimately looking for H plus, which we could write the rate expression for that guy, which is the rate is equal to also a reactant, -1/2 because of the coefficient. Change in concentration of H plus over the change in time. We actually do have our information here. So for I minus, so we can put it in. And if we do that, the rate is equal to -1/3. Remember that our final concentration for I minus is 0.868 as it's decreasing to that concentration. That's 0.868 minus 1 molar. Divided by, in this case, you can assume 0 was the initial time, seconds. And if we do all that there, we'll get 0.868 minus 1 divided by 10, and also divided by 3, which takes care of our stoichiometry. And we will get 0.0044. The units here are molar seconds, as they do not cancel up on top or the bottom. And that would actually be our average rate. Yeah. So it is a positive number because, again, when we do the subtraction up on top, it is a negative number along with the negative that is here, turning it into a positive. And that's what we would expect because that's a reactant. So it itself is changing negatively and losing over time. We are also interested in how H plus is changing over that time. So now that we actually have the rate here, that would actually be that number right there for our H plus. So we're actually looking for just that part of it, which tells us how the concentration of H plus over the concentration in time is changing. That means I need to do what with the 1/2? I need to multiply to the other side the 2. And we also need to take the negative with it as well, right? So we would actually have to multiply -2 to the other side times the rate that we just calculated. And that would get us -2 times 0. A couple of zeros there, 44 molar seconds. And we will end up with a negative 0.0088 molar seconds. Question on that there. Yeah. Because what we were looking for as part of the answer, the last part of it was how is the H plus over the change in time changing? So that is really what's in that box is what we needed to solve for. Yeah. And to do that, that's why the 2 went to the other side along with the negative, basically. So we basically multiplied this 1/2 by -2 to both sides. So those canceled, right? And that basically becomes 1 at that point. Yeah. And that got us down to here, basically. Question or good? Yeah. Okay. Other questions on that? So what we see here is the way that H plus is changing over time. It is actually changing twice as fast as the overall reaction, right, is happening, right? Overall, everybody's changing about 0.0044 molarity every second, but our H plus is actually changing twice as fast as that, right? So there are parts of the reaction that may be reacting more or less, and that's because of the coefficient, right? The mole-to-mole relationship and how they come together. So again, overall, as an overall reaction, everybody's changing roughly 0.0044 molarity per second. When we take everybody's individual sort of rate into account, that's overall average what they're all changing. Yeah. The -2 came from rearranging the rate expression for H plus, which was this. So if you just wrote it based off of the reaction, that was the rate expression. So what we were looking to solve for, which was the last thing that was asked, was actually just this part of it. So basically to keep that on that side, we have -0.5. So we had to multiply -2 basically to both sides. Those cancel, basically it becomes 1, and that gives us what we have down here. Other questions? Okay. Let's take a look at another one here. If you have 2.4 times 10 to the 2 grams of NOBr, the molar mass is 109.91 grams per mole. The mole there, that's up there. It decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes. Find the average rate of Br2 production in molarity per second. So we really want to know how much of this is being produced per second, basically. So we can write our two rate expressions from the equation, and that would be the rate is equal to -1/2. Again, because NOBRs are reactants, so that's where their negative is from. Change concentration of NOBr over change in time. We also could do it for our Br2, which would be the rate is equal to, in this case, it's a product, so it's going to be positive. Coefficient is also 1, so we don't have to worry about it. So it's just going to be Br2 over the change in time. So we do have information about NOBr that's decomposing. We really have grams, and we have volume, and we have the molar mass, which was nice of them to give. Otherwise, you would go to the periodic table, right, and look it up or calculate it. So we do want to convert really into molarity here for the NOBR. So we're going to take our grams, which is 2.4 times 10 to the 2 grams of NOBR. We then will use the molar mass from the periodic table, which is 109.91 grams per mole of NOBR. And that will get us and we'll call it 2.1836 moles of NOBR. I also want the molarity really of NOBR, so I'm going to divide it by the volume, and that is basically 200 milliliters. And there's 1,000 milliliters in a liter, which gives us 0.2 liters. So this would then be divided by 0.2 liters. And if we do that, we will end up with a concentration of NOBR that is 10.9, and I'll call it 1/8 molar. And in this case, since we are ultimately looking for seconds, our unit of times in minutes, so I'm also going to convert my minutes into seconds. At some point, you got to do that. So 5 minutes. There's hopefully 60 seconds, I think, in a minute. That is 300 seconds. So now that I calculated the molarity, I calculated really the time that we're talking about that changed. I really have everything I need on the right-hand side there to put it into the rate expression for the NOBR. And if we do that, the rate would equal -1/2, -10.918 divided by 300 seconds. Why did I make it negative? Yeah, and it's decomposing, it's a reactant. So basically how we would have got that number would have been like final minus initial, which should have gave us a negative number. So, and because it's a reactant, it should be negative. Otherwise, if you didn't do that, you will end up again with a negative rate here, which should be positive for the average rate of the reaction. Question on that there. So doing that, we would take not that, we would take maybe that divided by 300, also divided by 2. That's going to give us 0.018 molar seconds, as the units do not cancel. That would be our average rate in this reaction. That's really good because if we come up to our BR2 over time, we could see here that the concentration of BR2 over time, our change in it, equals the rate. So basically equals that number in this particular case. So the production of BR2 over the change in time is basically the same as the average rate here. Is basically what we're producing. Question on that there. Yeah. Yeah, it would probably be a good idea because that way you should have at least one piece of information that will allow you to really probably calculate the rate. Alternative to that, you could be just given the average rate for the reaction, and then you could be able to calculate how either the reactant or product is changing. But usually in this type of problem, getting the rates that are involved are really what you want to do. You don't, like I said before, here we didn't do anything with NO, so you don't need to bother with it or anything like that. So that's what I was saying before. We were just talking about just writing the rate expression where you can write it, set them all equal to each other. But really what you could do in a lot of problems is just concentrate on the ones that are kind of involved and not worry about the other ones that are there. Other questions? So this is one way that we do it. And again, taking 1 over the coefficient really kind of bundles in the stoichiometry part of the calculation with the kinetics part of the calculation. Just to show you, for example, in a problem like this, you can sort of do it as just like a stoichiometry problem first and then get the kinetics part of it. So if we were to just sort of do the stoichiometry part of it first, we would just pick up here where we got the moles of the NOBR. And we would take 2.1836 moles of NOBR. And then we would just do a normal mole to mole relationship like stoichiometry, where 2 moles of NOBR is equal to 1 mole of BR2. So we would just do that part of the calculation, just like a basic stoichiometry problem. 2 moles of NOBR and 1 mole of BR2, and that would get us 1.0918 moles of BR2. At this point that we just did the stoichiometry part, now we could just incorporate all the kinetics part of it, which would be, we would obviously want to do the liters part, right, to convert it into molarity. So we would take this and divide it by the 0.2, and that would get us 5.459 molarity, basically moles per liter. At that point, we then can divide by the time, which is 300 seconds. And that will then get us back to here, basically. So if you want to just kind of do a basic stoichiometry problem first, and then kind of incorporate all the kinetics part of it, convert it to molarity, and then divide by the time, you can do that as well, get you the same answer. Or you could do 1 over the coefficient, and it'll kind of do it all for you, you know, in one step-ish type of thing. Any questions on that there? Question on rate expressions. Yes. You need to be able to write them, obviously, and solve problems similar to this. So, all right, that's what we just did. So let's talk a little bit about rates and some of the things that can affect the rate of a reaction. So one thing that can affect the rate of reaction is the nature of the reactants. So what type of reactions do you have? Are they aqueous? Are they gases? What they may be. In general, small molecules do tend to react faster than larger molecules. Gases really do react faster than liquids because gases are flying around, right? So they're flying around, they have a lot of energy, they're bound to come in contact with other gases most likely, and that would obviously help kick off the reaction and have it occur. Uh, Obviously, liquids react faster than solids. Solids are pretty much just sitting there until you do something to help them out, like stir them, right, and mix them, provide some energy and stuff like that. So just throwing a solid into a beaker, a couple of solids into the beaker, probably not going to react all that fast, right? Unless you give it a little helping hand to sort of do that. In terms of solids, though, block solids react a lot slower than ones that are powdered or kind of spread out, right? You have kind of a surface area, a greater surface area for everything to come in contact with. Maybe in Chem 50, they still do the one where you tie the magnesium up with the string and you add the HCl to it and it bubbles off or until your magnesium goes free of your string. So I don't know, maybe some people in your class, if you really like coiled that magnesium super tight, it took forever for that reaction to take place because you hid the magnesium from the HCl. So it couldn't find it. If you kind of lightly coiled it with left a lot of surface area, allowed it to hit it, and obviously the reaction to take place. Certain reactions or chemicals do react faster than others. The activity series, maybe you're familiar with the activity series, usually talk about that when you talk about single replacement reactions, right? So in order for a reaction to take place, like a single replacement reaction, like zinc and hydrochloric acid, this guy comes in and kicks out the hydrogen, makes some hydrogen gas, plus some zinc chloride. But in order for this reaction to take place, zinc would have to be more reactive than hydrogen, which it is. If you do the same reaction with like copper, it will not take place because copper is less reactive than hydrogen. Ions usually react faster than molecules because where do we find ions typically? Ions are typically in what type of substance? Ions are typically in solutions, yeah? So when we look at solutions, you don't see anything, right? Because it's a homogeneous mixture, but they're full of ions basically floating around, right? And because they're already floating around in the solution, they're ready to go, right? You don't have to break any bonds, they're just ready to react. That's why when you take a solution, you add something to it that's insoluble or makes an insoluble product. When you add some other solution in, it makes those ions now floating around in the solution and they come together and perhaps makes a solid. Temperature is a really big factor in terms of kinetics and how fast or slow a reaction takes place. There's a couple of formulas we'll talk about later on in this chapter that involves temperature, but in general, increasing the temperature typically will increase the rate of the reaction. Because technically, when we increase the temperature, what are we actually adding to the reaction? Energy, right? And all reactions have a minimum amount of energy required for it to take place. That is what's known as the activation energy, right? And the activation energy is like the hill that those reactants has to climb to get to the other side. Not all reactions actually occur just as a result of two things coming together and hitting each other. They actually have to hit each other in the right location, and they have to have the right amount of energy to do that. Increasing the temperature gives a greater proportion of reaction molecules that can meet those terms. They have enough energy to get up and over basically to the other side. Typically, if you increase the reaction about 10 degrees Celsius, it usually will double in terms of how fast it will occur. The opposite is true. When we lower the temperature, we throw everything on ice. We're basically removing energy, right? So now there's a lower proportion of molecules that have enough energy really to get to the other side to make products, and that usually will slow down a reaction, right? The Arrhenius equation, which we'll talk about in this chapter, deals with that and sort of the relationship between temperature and the rate of reaction. Another common thing that can affect the rate of reaction is a catalyst. A catalyst is not a reactant. It is not a product. And it does not get used up. in a reaction. Really, the catalyst is there to facilitate the reaction basically happening, in most cases, faster. There are catalysts that are negative catalysts that slow down a reaction, but most of the time, when people talk about a catalyst, they're talking about it as speeding up the reaction. Catalysts typically find an alternative pathway for that reaction to take place. You typically can find catalysts written on top of the arrow. It could be like it's a solid catalyst, like a piece of metal, which maybe attracts everybody to that central location. And because everybody's now in the central location, they're going to start reacting a lot quicker than if they were just kind of floating around, or if they're gases or something like that, trying to find one another. Ultimately, as we'll talk about, how a catalyst works is that activation energy hill, they actually lowers the activation energy. So the hill to get to the other side comes down as a result of the catalyst being present, and thus there is a greater proportion of reactants that can actually get over that smaller hill, and that would see an increase in the rate of the reaction. As we'll talk about towards the end of this chapter, catalysts can be homogeneous, which means the catalyst is in the same phase as everybody that's reacting. Maybe they're all aqueous. So maybe sometimes we use acids as catalysts, sometimes bases as catalysts, and acid and bases are aqueous and your solutions are aqueous. So they're all in the same phase. As I mentioned before, they could also be heterogeneous, like the metal example. Metal's a solid, maybe all the reactants are gases, so they're in different phases and stuff like that. Other factors that can affect the rate are things like concentration. Generally, the larger the concentration of a reactant molecules, the faster they react. When we talk about something like molarity, which is moles per liter, and we talk about something like a solution, right? There are two parts to the solution, right? There's the solute, which is the smaller part, and there's the solvent, which is the larger part. When we talk about a reaction that takes place with solutions, which part of the solution actually reacts? Is it both parts? Is it just the solute? Is it just the solvent? What's actually reacting in the solution? It's really the solute, right? And what molarity is really moles of solute, right, over liters of solution. So if you have a large molarity, that means you have a lot more solute in that solution, which means, again, there's going to be greater opportunity for everybody to start to react, and the reaction will occur a lot quicker. Again, that larger molarity does increase, obviously, the contact between reactant molecules. The concentration of gases depends on the partial pressure of gases. Higher pressure, higher concentration. That's also because when we have a high pressure, as we talked about the other day, the volume is high pressure, you have small volume. Yeah, Boyle's law. So higher the pressure, smaller the volume. And because the volume is smaller in those situations, that means our gas molecules are all, again, pretty much near each other. So that's going to increase their interaction. That's going to increase the reaction rate that's going to occur. Any questions on that there? All right, so let's talk officially about the rate law. So the rate law is a little bit different than the rate expression that we've been talking about. The rate law expresses the relationship of the rate of the reaction and its rate constant to certain powers. So if we have a reaction such as the one we see here, we could write the rate law, which is this. The rate is equal to K. K is our rate constant. These are our concentrations of A and B, which are our reactants. X and Y, as it says on the bottom there, those are what are referred to as orders of a reaction. First important thing that we see in terms of the rate law and how it's a little bit different than the rate expression is, what are the only things involved in the rate law? A and B are reactants, yeah? So only the reactants in the rate law, no products. So it's all about the reactants when we write a rate law. The other thing is X and Y are the orders with respect to A and B. So X is the order with respect to A, Y is the order with respect to B. They are found experimentally. So all rate laws are pretty much found experimentally, as we will shortly see. That means you will typically be given a table of values and you have to do some type of calculation to figure it out. We can also figure out the overall order of a reaction by actually adding the individual orders together. So if you added X and Y together, maybe they're each first order, and the overall order would then be second order for that reaction by 1 + 1 = 2. So what are the orders and, the relationship there, as we talked about the rate constant sort of tells you how fast the reaction is taking place. X and Y, which are the orders, are sort of the proportion of each of those reactants that you need to maintain that particular rate. And it can affect things. So for example, let's just say we had a rate law that was K is times A times B. In this case, the order here would be 1 and 1. The overall order would be second order in this case. By adding 1 + 1 would give us our overall order second. So let's say that we did this reaction and we had basically the concentration of A was 2 molar and the concentration of B was also, we'll go with 2 molar, right? So if we put those values into this, and we're going to just, it's a rate constant, so it's going to be a constant number no matter what. So I'm not going to worry about the rate constant at this point. So if I put that in there, I basically get a rate of 2 × 2, which gives me 4 molar, and we'll put the seconds in there. So with the rate constant, we would have the seconds part of it in there. So basically we get like 4. So let's say I wanted to double the concentration of B I used in, let's say, another experiment. And if I double the concentration of B in this case, and I left A constant, that's the same concentration of 2A, 2 molar for A, and I'm just making these numbers up, by the way, 4 molar there for B. Now, when I calculate my rate, I would have basically 2 × 4, which is 8 molar seconds as my rate. In this particular reaction with this rate law, when I doubled the concentration, what happened to the rate? The rate went from 4 to 8. It also doubled in this case, right? So if I wanted to, and I knew the rate law for this particular reaction, and I'm like, it's taking like way too long for this reaction to take place, I could increase the concentration of A by doubling it, and it then should happen twice as fast as this particular reaction. Now, sometimes maybe you do a reaction, which may happen when we actually do our kinetics experiment. It happens very often. Like you're a little too slow to get the thing in the spectrophotometer, and the reaction's over by the time you get there. So maybe it happens like way too fast. So let's just say, well, all right, I'm going to cut my concentration of B from 2 molar, which originally was, down to 1 molar, right? So now when I put it into my rate law, I basically have 2 × 1, which gives me 2 molar seconds. In this case, by cutting the concentration of B in half, how did it affect the rate from the original reaction? It was started at 4, right? With 2 molar each, cutting the concentration in half, cut the rate in half in this case, right? So I was able to slow down the reaction by a full factor of 2, right? Which might give you a little bit more time, right? As you're doing the experiment. Now, let's say we were actually dealing with a different type of reaction where maybe the rate law was K is A and B squared, right? So in this case, the overall order would be 1 + 2, which means it would be a third order reaction overall by adding the individual orders together. So now let's just compare. If we use the same concentrations as we did in that reaction, that A is 2 and B is 2, that would give us a rate that's equal to 2 × 2 squared, right? So that's 2 squared is 4. 4 × 2 is 8 molar seconds for our rate. Now, using the exact same concentration as we did in the first experiment, our reaction versus this reaction, by the order being 2 there for B, we see that the reaction has now doubled, right, from the original reaction, because we have kind of the second order there for B. Now, if I decided, like we did before, to come here and double my concentration of B, that would mean that the rate would equal 2 times 4 squared. 4 squared is 16, right? 16 times 2 is 32 molar seconds. Now, between my original concentration and just doubling it in this reaction, my rate went up by a factor of 4, yeah? And vice versa, if we lowered the concentration of B down to 1, we would actually see it drop the other way, right, by a factor of 4. So what the orders are, they're basically, again, the proportion of each of those reactants that you need to maintain a particular rate. And the benefits, if you kind of know what the orders are and which one is affecting a reaction more than the other, you can play with that concentration and really kind of tailor your reaction to how fast or slow you may need it. Because a lot of times, like I said, in real life, you may do a reaction and it may just happen like way too fast for you to do any type of measurements and stuff like that. By the way, if I had a rate law that was something like this, the rate is equal to K A and B to the 0. The overall order here would be 1 plus 0, which would be first order here, right? Now, in this case, right, when I put my concentrations like it was originally here, 2 for each, I would have 2 times 2 to the 0. When you take something to the 0 power, it equals 1, which means my rate here would be 2 molar seconds. In this case, my rate was actually now half of what it was before because the order for B was actually 0. If I increase the concentration of B to like 20 molar, would it make it a difference? It would not in this case. So in this reaction, if that was the rate law, B has really nothing to do with the rate of the reaction. You can do whatever you want to be. It will not affect the rate of the reaction. If you wanted to affect the rate of that reaction, you would need to work on A, right? A was the only thing that's basically there that would affect the overall rate of that reaction. Any questions on that there? Yeah. So how do we go about figuring out the orders of everybody? Again, it is found experimentally. So typically what we do is you could do it one of two ways. You can look at the table and if you understand how concentration changes and rate changes, you can figure it out. My experience is most people don't know how to do that properly. So maybe a mathematical approach would be a better approach. So you could take the rate 2 over the rate 1 is equal to K times A to the X, B to the Y, and K A to the X and B to the Y. So when we say rate 2 and rate 1, this is a typical type of table that you may be given in these type of problems. May have 3 entries like this, may have 4, 5, 6, a bunch of entries. But typically what you will have is the concentration of each of the reactants given to you for each of the experiments. That's like experiment 1, experiment 2, experiment 3. And you'll typically have the initial rates given to you for each of those things. So when it says rate 2 and rate 1, it doesn't mean that you go to the table and always take number 1 and number 2 entry. It means you just go to the table and find 2 entries. When you go to the table, what you are looking for is 2 entries where one of the concentrations of the reactants stays constant and the other one varies. Otherwise, you will have too many unknowns. Yeah. So to keep the number of unknowns to a minimum, you want to find 2 where they stay the same, one of the concentrations, and 1 where it varied. So for example, if we were to look at experiments 1 and 2 here, we see that the concentration of F2 remains constant, but the concentration of the ClO2 basically varies. So we will put these into our math here. Personally, I go with the larger rate up on top. And typically what that will give you is nicer whole numbers. You can do it the other way, but you'll get some decimal numbers. But usually if you kind of put the larger rate up on top, it'll be better. So I'm going to put everything for experiment number 2 up on top. So 4.8 times 10 to the minus 3 equals K times the concentration of 0.1, which is our F2 to the X, and 0.04 to the y. So everything that I wrote up on top here comes from experiment number 2. I'm going to put everything for experiment number 1 on the bottom, which is 1.2 times 10 to the minus 3, k, 0.1 to the x, 0.01 to the y. Any questions on that? And again, it just happens to be 1 and 2 in this case, but the purpose of why we chose that is these guys were constant. At this point, we're going to do some math. So this guy divides out to something there. That's a 4, I think. Yeah. Who would have thought? This is a rate constant, right? And that is a rate constant. The name is a rate constant. So should that number be the same or different? Although we don't know what it is at this point, we do know that it is the same and it should cancel out. This is the order with respect to F2, and this is the order with respect to F2, and it is the same reaction. So again, although we don't know what it is at this point, should be the same number. So these guys will cancel out. And we do this division here, we will get 4 to the y. Yeah. At this point, you could probably just visually see that y should equal 1. By the way, if you don't have pretty numbers like this, you could take the natural log of both sides. And when you do that, the y will come down, and then you can divide by the natural log of both sides. And you'll end up with 1. So if you don't have pretty numbers, you can't visually see it, natural log both sides, and then divide it out. And that's really how you kind of get there. So that tells us that the order for ClO2 is first order. We then would go back to the table and choose 2 other entries where we now will keep the ClO2 constant and we will vary the F2. So in this particular reaction, it looks like number 1 and number 3 will do that. That will keep those guys constant and vary the other 1 and 3. Once again, I'm going to put the larger rate up on top, which is 2.4 times 10 to the minus 3 equals k 0.2 to the x and 0.01 to the y. I just put in there everything from entry number 3 up on top. We're going to then divide it out for entry number 1, which is 1.2 times 10 to the minus 3, or k, 0.1 to the x and 0.01 to the y. Once again, doing some math here, that's going to divide out to a 2. Once again, our k's are going to cancel. These guys will cancel out to 2 to the x, and these guys will completely cancel out. And that's going to give us here, as you could guess, x is equal to 1 as well. That means the concentration of the order for F2 will also equal 1. We've now figured out the orders for each of the reactants. That means the overall order here would be 1 plus 1 is second order. And we could write the completed rate law, which in this case would be the rate is equal to K times F2 and ClO2 here. Questions on that there? We'll do it next time, but at this point, now that we actually have the completed rate law with the actual orders, we could then use the table to go back and solve for the value of the rate constant. And you can do that by choosing any of the entries and putting the numbers in and solving for K, and that would give you the value of the rate constant. But I think we will lay it up there for today. Any questions on that there?